Greetings and welcome. In today's video, I'm going to discuss polar coordinates, how to graph points, find distances between points, and talk about some basic functions in the polar coordinate plane. So the first thing I want to do is kind of consider the following. Cartesian coordinates problem. So if I want to plot the point, say 3, 4. If I want to plot the point 3, 4, on the Cartesian coordinate system, what we would do is move 3 in the x direction, right, because that was the x coordinate, and then move 4 in the y direction, and plot our point, right? So over 3, up 4, and there would be our point, right, 3, 4. In the polar coordinate system, we're going to locate the same point but using two different pieces of information, right? In Cartesian, this was kind of horizontal location and then the vertical location, where this time what we're going to do is base it off of an angle measurement. So we'll use theta as our angle, typically measured off of the positive x-axis. And the other dimension that we'll use is the distance. So this distance here will be r. And with those two pieces of information, we'll be able to find exactly the same points that the Cartesian coordinate represents. Every point on the plane can be located with these two pieces of information. And there's kind of like somewhat of a one-to-one relationship between these. So our polar coordinate system will be of the form r, theta, where r is the distance from the origin, or the pole, to the point, or the magnitude, I guess you could kind of think about it. It's similar to when we dealt with vectors. And theta is the angle from the positive x-axis, which is also known as the polar axis. So let's talk about this particular example where we've got this triangle here was 3, 4. If I use Pythagorean theorem, r would equal 5. And theta, I could actually use any trig ratio to convert and find the particular theta value. So this point is, well, I guess we'll figure that out. We'll do that real quick. So let's see. So from theta's perspective, 4 is the opposite, 3 is the adjacent, 5 is the hypotenuse. Let's base it off of 4 and 3, the values that we'd started with. So I could say tan of theta is equal to 4/3. So theta must equal the tan inverse of 4/3. So in this problem, theta would equal, let's see, second tan inverse, 4/3. 53.13 degrees. Something about that, actually, yeah, so that's squeakle sign, technically. So this point could be referred to as 5, 53.13 degrees, roughly. And that's how I could locate that point. Alright, so let me show you what the polar coordinate system actually looks like. So polar coordinate system, also known as the polar plane. And instead of kind of having a rectangular system, what I'm going to do is kind of have a whole bunch of concentric circles. And my circles aren't perfect, but they'll express the point. And let's see, so let's label what we've got. So this axis will be the polar axis. The center, where the origin used to be, is now called the pole. Alright, think of like North Pole, South Pole on the globe. And then to plot a particular point, I'll move by a particular angle. So for instance, here's 90 degrees, or pi over 2 in radians. Here's 180 degrees, or pi. Here's 270 degrees, or 3 pi over 2. And here's 0 degrees, or 360 degrees, which is the same as 2 pi. And so I'm able to represent any point. Let's see, typically I'll have kind of, instead of tick marks representing y-axis values or things like that, we'd be interested in kind of angle marks, I guess, from the polar axis. So for instance, if I wanted to plot a point, let's consider, let's say 3, 250. The way I would plot that is starting here. I could go out to 3, 1, 2, 3, and then move around the 3 radius circle all the way to 250, which is probably somewhere around here. All right, and there would be that point. So this is 250 degrees and a radius of 3. Or if I wanted to plot the point like 2.5 at 250 degrees, then I'd have just moved over 2.5 points and bend 2.5 units here, things like that. So it turns out R can be positive or negative. So in the case of it being negative, I would just move in the opposite ray from 250. So if I wanted to plot negative 2, 250, I'd go out 250, but then instead of moving forward 2, I'd move backwards 2. Something like that, and I could plot that point that way. And then the theta value, I think, will typically be measured in radians for us, but can also be measured in degrees. And we could technically have negative values, positive values, anything like that. So let's plot a couple points real quick. And for these, I'm going to steal some grids from Geometer's Sketchpad. So let's see, plot the following. Let's see. So here's a little grid. So let's plot the points. Let's do 4.5, 70 degrees. Let's do negative 2, pi over 4, and let's do well, let's make it crazy. Square root of 2, and we'll do 5 pi over 2, something like that. And just for fun, let's label these A, B, and C. So to plot these, so this first one, I'd start at the pole and move out 4.5. So 1, 2, 3, 4.5. So you can kind of imagine the 4.5 radius circle the whole way around. And I want to go to 70 degrees. And let's see. So here's 90 degrees. I believe this would be our 45 degree mark, right? So here's 45 degrees. Here's 90. And let's see if I divide that into thirds. I believe these are 15 degree increments. So here's 30, here's 15. And then this would be 50, 60, and 75, something like that. So to plot this point out at 4.5, I'm going to go to 70 degrees, which is somewhere right about here. Would be point A. Right about there. To find point B, in this case, yeah, I could go out to negative 2 and then rotate, but I'll actually prefer to move by the angle first. So pi over 4, let's see, this is pi over 2, so pi over 4 is the same as 45 degrees. So let's get to pi over 2 first, and then instead of moving out in this direction, the positive direction, I'm going to move in the negative direction. So that's going to be out here, and negative 2 is right there. So that would be my point B. right there. And one of the things you might be realizing is there's probably another way I could label point B, and you're absolutely correct. And it turns out that there's going to be infinitely many ways that I can label any point within the polar coordinate system. Oh, let's see. Here we are. So let's see, and then let's lastly look at this one, the square root of 2, comma 5 pi over 2. So the square root of 2 is about 1.414, just so you know. And 5 pi over 2, well, let's see, is, well, I guess I could convert it, but, so 1.414 is probably around here-ish, and let's see, so here's pi over 2, here's 2 pi over 2, 3 pi over 2, 4 pi over 2, and 5 pi over 2 would land me back up on kind of the pi over 2 point right there as far as the degree. So pi over 2 is coterminal with that, or 90 degrees is coterminal with that, is another way I could say it. And there's point C. So I just want to point that out that, so this is also the same as technically 1.414, and pi over 2 would land in the same location if I was rounding for the value of the square root of 2. So yeah, so let's consider the fact that you can represent these in multiple ways. Actually, I think what I'm going to do, for sake of time, is just steal a snapshot right here, and then just explain it. So you can pause the video if you want to be able to write this down. So let's see, multiple representations of our r comma theta. So if a point P has polar coordinates r comma theta, then P can also be represented by the polar coordinates r comma theta plus 2 pi k. So 2 pi is equivalent to 180 degrees, or 1 full revolution of a circle. And then k is just some multiple. It says later that k is any integer. So it could be 1 revolution, 7 revolutions, -2 revolutions around the circle. And basically, these are coterminal angles to the original theta. So I can have any multiple number of rotations around my circle landing in exactly the same point. So that in itself would be infinitely many values. Now this one's a little bit more interesting. So instead of r, they're saying we could move backwards r units. If I take my original angle and add 2k plus 1, which I don't know if you know this, but the definition of an odd number is 2n plus 1, where n is an element of the integers. So basically they're saying adding an odd number of pi, all right, and pi is 180 degrees, or a half revolution around a circle. So if I add any odd number of pi, that's going to, well, let's actually consider that on our previous sketch. So B here, we considered being out at, what was it, pi over 4. But if I add an odd number of pi, or 180 degrees, right, I would have landed on the same value. Or if I add another 180 degrees, or actually no, that would be an even number of pi, wouldn't it, right? That'd be 2. So if I spin around 3 times, or 5 times, I can land in the same location. And basically I can represent it by being 180 degrees away angle-wise, but just moving in the opposite direction, is all that that's saying. So this is just basically indicating that there's infinitely many ways of representing a point in the polar coordinate system, unlike the Cartesian coordinate system, where you would just represent it as your ordered pair, horizontal and vertical movement. Let's see, the next thing I want to look at are some basic functions. So let's see, graphing basic functions. So in the Cartesian coordinate system, if I gave you the equation y equals x, it's basically saying consider all possible values of x and y that make that equation true. And graphically speaking, that's going to be a line that is diagonal, right? Slope of 1, up 1 over 1, and is a vertical line. If I want to graph the equation r equals 3 on the polar coordinate system, let's see, let me once again steal a snapshot from a graph. Let's consider what are the set of all points that have r equal to 3. So theta equaling 0 and 3 is a point. Theta equaling 30 degrees or 45 degrees, right? Or theta equaling 90 degrees or 105 degrees. Theta equaling 180 or 270. All of these points are going to be possible solutions of this equation. And so you can see that if I say r equals 3, it appears as though my graph would just be the set of all points that are 3 units away for any value theta, which ends up being the graph of a circle. So that's kind of an interesting value. Another equation, a basic equation I could have, is what if I say theta equals 150 degrees. Let's get another coordinate plane here. I guess polar plane is more accurate. So let's consider all points that have 150 degrees as their theta, I guess, coordinate. So 150 degrees from the right polar axis here would be, let's see, here's 90, 105, let's see, 120, 135, and I think here's 150. So here's the point 2, 150. Here's the point 1, 150. Here's the point 5, 150, or 7, 150, or 4.5, 150. And then I could also have 0, 150, or negative 1, 150, or negative 5, 150. And you see what I end up getting is the set of all points, right, that form a 150 degree angle with the positive x-axis, or with my polar axis there. And then also kind of all of the negative values there as well. So this equation, if I have just theta equals a number, right, an angle in this case, I'll get the graph of a line. So those are some basic graphs of polar equations. And let's see, the last type of problem that I want us to consider is the distance between 2 points. On the polar coordinate system. And so this is kind of an interesting case. Let me start off with some grid here. So let's consider if I have this point right here is point 1, and this point is some r number of units away at some angle theta. I'll call it theta 1 and r1, right? So there's my first point. And then here's my second point. Let's see, I think I'll do orange. It'll show up better. And let's say here's point 2. All right, and that is, we'll call it r2 units away at an angle theta 2. And I want to find the distance between these 2 points. All right, so the distance would be the shortest possible distance, being a straight line, of course. So let's consider what that would be. So let's see, we'll call this point 1, point 2. Let me get a drink of water. You guys can draw a picture of this graph in the meantime. And take a look at this situation. So what I'm left with is a triangle, not necessarily a right triangle, and I can find a couple pieces of information. This angle here is going to be theta 1 minus theta 2. right? So the big angle minus the little angle will leave me the remaining scrap. And then I know these two sides, the R1 and R2 values. So if I want the distance, I've got a triangle here, and I'm going to be able to just use the law of cosines. So the distance formula on the polar plane is going to look like this. It's just going to be the law of cosines, right? So the distance from point 1 to point 2 is going to equal the square root of, and what do we have? We'll have R1 squared plus R2 squared minus 2R1 times R2 times cosine, and my angle is theta 1 minus theta 2. And that's going to just give me that distance. It's just directly the law of cosines that's giving us that. And that kind of makes sense if you think about the Cartesian coordinate system, and the distance formula in that case, whether you know it or not, is actually directly related to the Pythagorean theorem, and finding that kind of hypotenuse of the triangle formed by those 2 points. So it would make sense that in this case, since I know kind of some angles and some sides, that it would be another means of solving some triangle. But in this case, a right triangle is not the most convenient for us to work with. This kind of whatever acute or obtuse or whatever kind of triangle it ends up being will end up being the most beneficial. So this, I just want to point out, is directly from law of cosines. And in the interest of keeping this video a little bit short, I don't think I'll do an example of this, since I believe at this point you guys are all familiar with the law of cosines. And an individual could just kind of plug in the values of R1, R2, and theta 1 and theta 2 into this formula and get it from there. Alright, so thanks for watching this video, and I'll talk to you guys later.